Welcome back to today's video. In the last videos, we've talked about orthogonal projection, and you might remember that one of the important things for being able to compute an orthogonal projection was having an orthonormal basis. In this video, we'll be talking about a method that computes an orthonormal basis. This method is called Gram-Schmidt Orthogonalization, or Gram-Schmidt Orthogonalization as well. So the goal here is to find an orthonormal basis for a vector space. The idea is the following. We'll start with any basis. So we assume the vector space is given by some basis. And we'll just call this basis V1 to Vn. Now in the first step, we're going to find an orthonormal basis for just the vector space spanned by V1, the first basis vector. That's easy. We just have to normalize V1 to do that. So we set B1 to V1 over the norm of V1. We just normalize, and there we have our basis vector. And then the span of our basis vector B1 is of course the same as that of V1. We just rescale that vector. Now we have an orthonormal basis for a part of that vector space that we're looking at. And now let's take the second vector, the V2. We can decompose that second vector into a part that is parallel to the space that we already have, parallel to B1 in that case, plus a part that is orthogonal to this. And of course, we're only interested in the orthogonal part because the part that is parallel to B1 is already cared for by B1. We don't need that anymore. So the next is we want to find an O and B for the vector space spanned by V1 and V2. And to do this, we compute the decomposition of V2. We decompose V2 into U and U ortho, where U is contained in span B1, and U ortho is contained in the orthogonal complement to that. And then we just keep this orthogonal complement. So we set our vector B2 prime equal to U ortho. And then we normalize that to get B2. Now if we did that, we have made sure that the span of B1 and B2 is equal to the span of V1 and V2. And at the same time, the set B1 and B2 is orthonormal. That means in the next step, we can then decompose V3 using this orthonormal base of the partial space that we already have, and just continue in the very same way. So we'll just continue doing this until we have processed all the vectors, and that will give us an orthonormal basis. So that procedure is known as Gram-Schmidt. And let's write that down more formally. So that is the Gram-Schmidt Orthogonalization. And it basically works for all finite dimensional vector spaces that have a scalar product. But of course, we primarily use it for R to the n and subspaces of that one. So let V be a Euclidean vector space, as always. So we have a finite dimensional vector space equipped with a scalar product. And let V1 to Vn be an arbitrary basis of that space. Then the following procedure determines an orthonormal base of V. And this orthonormal base, we call that B1 to Bn. What we do is, for starters, we'll set B1 equal to V1 divided by its norm. So we just normalize the first vector. And then we repeat the following step. So starting at the second vector up to vector n, we compute successively the following vectors here. We start with the vector bk prime, and that is defined as this U-ortho part of the decomposition. So that is obtained by taking vk and then subtracting the orthogonal projection of vk onto the space spanned by the b vectors, b1, b2, and so on, that we already have. So we already have all the vectors from 1 up to k minus 1. And the orthogonal projection is computed, as you know, by taking the scalar products of the vk with the bi's that we have already times bi. So that's the formula for the orthogonal projection, right? So this here, what happens here is, this is the orthogonal projection of vk onto the span of b1 to bk minus 1. So if we subtract vk minus that projection, we get this U-ortho part, right? So we throw away the projection part, we keep the orthogonal part of the vector vk. And that's our new basis vector. Basically, the one thing we'll have to do is we have to normalize it. So please do not forget normalization, because for this formula to work, for this to be the projection, you know, you need an orthonormal base of this space here. So if you don't normalize, you will not have an orthonormal space, and that means all the following vectors will be wrong. So this is an essential part, this normalization step. Although it sometimes leads to not very nice numbers, it's an essential part here. So that is all that is to Gram-Schmidt orthonormalization, actually. Let's summarize this in a quick theorem, and then we'll see an example. So we've seen the procedure already, theorem, but two easy consequences of that one. The first consequence is this procedure can be applied in every situation where we have a finite basis, finite dimensional vector space. So every Euclidean vector space actually has an orthonormal basis. And the second consequence is, if we have a Euclidean vector space and a subspace of that, then we can always find a basis of a whole space, that is an ONB, such that the first part of that ONB is an ONB of the linear subspace, and the second part is then an ONB of the orthogonal complement of that subspace. Let's write it down. That's probably easier if you write it down slowly. So let V be a Euclidean vector space and U be a linear subspace. And let's say the dimension of a linear subspace is K. And what we say is that there exists an ONB B1 to Bn of V such that the first part B1 to Bk is an ONB of U, and the second part Bk plus 1 to Bn is an ONB of the orthogonal complement of U. And this answers the question of how to compute a basis for an orthogonal complement. You start with a basis of U. You extend it to have a basis of V, and then you apply Gram-Schmidt orthogonalization. Now, the vectors, the first part, the basis of U, will turn into an ONB of U, and the rest will then be an ONB of U ortho. Okay, let's finally look at an example of how to compute Gram-Schmidt. We'll consider a vector space called U that is spanned by two vectors in R3. So that's a subset of R3. Geometrically, we're talking about a plane here. And we want to compute an ONB of U and also one of U ortho. Now, to do this, let's start with the ONB of U first. First step is just to normalize the first vector here. This here is our first vector, 1, 0, 1. So we normalize that. B1 is defined as 1, 0, 1 over the norm of 1, 0, 1. That norm is square root of 2. So this here is our first basis vector, 1 over square root of 2 times 1, 0, 1. Second step, let's compute B2 prime. That is simply V2. So we call this one V2 here. And this V1. So we have V2 minus the scalar product of V2 and B1 times B1. So what we get is v2 is 2 minus 2, 0, minus the scalar product of 2 minus 2, 0, and b1, that is 1 over the square root of 2 times 101 times 1 over the square root of 2 times 101. So that's what we need to compute. First thing you should notice is we have this factor 1 over square root of 2 here and here. And as you know, the scalar product is bilinear, so we can take out this factor. And of course, we can also move this factor here to the front of this whole expression. So we can rewrite this a little by saying, well, this is 1 over the square root of 2 times 1 over the square root of 2 times our scalar product, 2 minus 2, 0, and 1, 0, 1, times the vector 1, 0, 1. So we get 2 minus 2, 0, minus, now these two square roots here, that's just 1 over 2. The scalar product, that is 2 plus 0 plus 0, and then we have the vector 1, 0, 1. So we end up with 2 minus 2, 0, minus 1, 0, 1, and that is 1 minus 2 minus 1. Quick check here. We want to know whether that result vector here, this one here, whether this is actually orthogonal to the first basis vector. It was 101. The lengths don't matter for orthogonality, so I'm just leaving out those factors. And the result here is 1 minus 1, so that's 0, right? You should always make this quick check. If that does not yield 0, then you have made a mistake. And please correct that before you go on. Otherwise, all the rest will be totally wrong. Okay, we're still good. So next thing we do is we compute the norm of b2 prime. That is the square root of 1 plus 4 plus 1. So square root of 6. And that means b2 will be defined as 1 over the norm times b2 prime. So we have 1 over square root of 6 times 1 minus 2 minus 1. And that's our second basis vector. So here's our O and B for U. 1 over square root of 2, 1, 0, 1. And 1 over square root of 6, 1 minus 2 minus 1. Now, the problem statement asks for O and B of the orthogonal complement of U as well. So let's continue with the process. We have this basis of U. Now we just need to add at least one more vector to get a basis of R3 and then continue Gram-Schmidt's method with that one vector. So that's step number 3 then. We add a vector that we believe yields a basis with those two here. So we just add that to the basis. And then we orthonormalize again. So the next step is then b3 prime is this new vector minus the scalar product of this new vector and our vector b1. Let's watch this one here. Minus, and now we have to take b2 into account as well. The scalar product of this new vector and our b2. And remember, we always have to use the scaled, so the normalized versions here. Otherwise, the results will be wrong. Okay, so that's what we have to compute here. Let's see, what do we get? We get 0, 0, 1, of course, minus 1 over 2 times, that scalar product is 1 times 1, 0, 1. And here we have minus 1 over 6. Then the scalar product is minus 1 times 1 minus 2 minus 1. So let's see, we end up with, let's add the first two vectors first. That is minus 1 over 2, 0, and 1 over 2. And then the second one, that's plus 1 over 6 times 1 minus 2 minus 1. So the end result, let's see, minus 3 over 6 plus 1 over 6, that's minus 2 over 6. Here we have 0 minus 2 over 6, that's of course minus 2 over 6. And finally, 3 over 6 minus 3 over 6, that's plus 2 over 6. 2 over 6 is 1/3. So in the end, we get 1/3 times minus 1 minus 1, 1. And now we have to normalize that. So let's compute the norm of B3 prime. The norm of B3 prime is, well, the norm of 1/3 times the norm of minus 1 minus 1, 1. So we can just take out that constant factor 1 over 3 out of the norm. So there's 1/3 times the square root of 3. And that means B3 will be 1 over the square root of 3 times minus 1 minus 1, 1. Again, quick check, minus 1 minus 1, 1, is that actually orthogonal to the vectors we had before? Minus 1 plus 1, that works. And here we have minus 1 plus 2 minus 1, so that works as well. Okay, so that is actually orthogonal, and that means this B3 here, that is then a basis of U ortho. So 1 over the square root of 3 minus 1 minus 1, 1 is an ONB of U ortho. And that completes this example. As usual, there will be a couple more examples in the exercise sheets, and we'll discuss some more in the central exercise sessions. So I hope I'll see you there. And of course, I also hope I'll see you in the upcoming videos. We will wrap up this whole topic by having a look at angles and also by using projections to get so-called least squares solutions. So to find an approximate solution to a linear system that does not actually have a feasible solution. So this will be the topic of the upcoming videos, and as usual, I'll see you then.